radioactivity, but what it means is that the nucleus, that center of the atom, is not stable, and it spontaneously decomposes or breaks apart and can give off alpha, beta, or gamma. Alpha particles or beta particles, which essentially is just an electron, or it can give off gamma radiation. Okay, usually it's these higher ones, and there's a term for these, and this was the new part, the new term here, isotope. Okay, the term isotope in everyday usage is just, if you've heard it at all, it's probably from the medical field. When they talk about isotopes, they're using isotopes in cancer treatment, they're talking about radioactive isotopes. Like that is a radioactive isotope. But in everyday life, we've connected those terms so well, everybody thinks every isotope is radioactive. Not true at all. The definition is same atomic number, but different atomic mass. Okay, here's your basic definition. Same atomic number, but different atomic mass. So, now meet this guy out of the discussion, because forming an ion, that's another story. These three, I can refer to these as the three isotopes of hydrogen, or this is an isotope of the more common hydrogen. So same atomic number, different atomic mass. Now let's see what that means. Andrew, take it. Take deuterium and fire off across.
One.
Mm-hmm.
One.
Mass?
Yeah, one. Oh, two. Sorry.
Okay. Make your adjustment.
Yeah, sorry. One.
Okay.
One.
Good.
One.
Hmm?
And what is? No, I got confused.
Okay. What's the charge of a proton?
Plus one.
Plus one. How many protons you got?
Okay. So plus one and minus one.
Yeah. Because your electron is negative,
Okay.
and that means your net is 0. Okay, so for isotopes, where does the difference lie? In the nucleus. And it's going to be with your number of neutrons. Remember, neutrons contribute mass, but they don't contribute charge. So it just makes a heavier nucleus. Okay, let's do tritium here. Let's just fire off across and do them all. Hina, hit it. 1, 3, 1, 2,
negative 1, or sorry, 1, plus 1, negative 1, and 0.
Very good, very good. This is just a little side story. You may have heard of heavy water. And heavy water, what they mean, and that's totally different than hard water. When people say hard water, they mean there's salts and stuff in their water supply. Heavy water, instead of being made with regular hydrogen, it's made with deuterium instead. So hence, it's a bit heavier than regular water. So that's what they're talking about. In graduate school, I did most of my research with, well, we refer to it as deuterated compounds, in other words, putting deuterium in. So I worked with a load of heavy water. We would buy it in small bottles and work with it. It's not radioactive, it looks like water, smells like water, and if I tasted it, it tastes like water, supposedly.
What happens if you drink it?
Okay, this is where my story's going. Okay, for writing a novel only. If you had this rich old uncle, and you were taking care of him, and you really wanted him to die so you could inherit his money, what you could do is use heavy water. When you make the old guy tea, make it with heavy water, not regular water. Okay, if you're making him coffee, make it with heavy water. Anything, making him soup, use heavy water for the liquid. What happens is when you drink heavy water, and they have found, at least when I was in graduate school, which is a long time ago, that nothing could survive by ingesting the heavy water. Not even a fish in, a bowl could survive in heavy water. Here's why. This is what the thinking is. If you drink that water, in your body you've got these thousands and thousands of chemical compounds that have to do things. Okay, a deuterium, a heavy hydrogen from that water, could substitute into a very important compound in your body and have now a carbon hydrogen bond. Okay, a carbon-hydrogen bond breaks a little easier than a carbon-deuterium bond. Well, if the carbon-deuterium bond is harder to break, it means a slower reaction. And so what's going to happen to the person is they're just going to slow down and die. And I've heard it happens fairly quickly. Now, that to me would be the perfect murder. Because no pathologist in the world would be looking for deuterium in this guy's body. You know, it just looked like, you know, they slowed down and died of natural causes. But every chemical reaction's going slower. What would get you is the paper trail, because you had to buy this. And they'd start questioning, you know, why is this person buying so much heavy water? Or if you were making your own, because a certain amount of seawater has the heavy water, you would have to distill, you know, I don't know how many tank cars of ocean water to get it, and that would take you so long, you just want to shoot the guy. So, anyway, it's an interesting usage. And 2 years ago, they used to sell it, chemical companies would sell disreputable people compounds with heavy water in it, because if they were running an illegal chemical lab out of their garage, okay, and they're using heavy water, that would show up in their products. Okay, and then the FBI would know enough to test. Okay, you think the guy's working out of Houston. Where is this heavy water showing up? New Orleans, Chicago, and so you can see distribution routes that way. And it's not radioactive, so it's not a health hazard for the people, you know, who might come in contact with it, but they can trace with that. Also in medicine, this is a great trace because this one's radioactive. So if you synthesize a compound and you think it's some new cure for some disease, okay, you synthesize the compound again, but you substitute in some tritium in for regular hydrogen. Test it on your animals, see where in the body that stuff's going. So you feed it to your animals for a while, rats or something, rats or mice, sacrifice your animal, which is medical talk for murder. Okay, sacrifice your animal and see, did the radioactivity all show up in the adrenal glands? Did it all show up in the liver? Or did it all show up within 24 hours in the bottom of the cage in urine and feces? It's not going targeting an organ in the body. So it's a great medical tracer, too. So, isotopes. You didn't need to know all that side story, but it makes it more interesting to see usages of these other isotopes. So know that definition. Now, if I have this and this, are those isotopes of each other? No. Because here you've got atomic number 1, that's the same, great, but the mass is the same. All we have is neutral atom and ion. Let's fire through here. If we have a hydrogen ion, let's go through and see what we've got. Pedro, hit it.
1,
Okay?
1,
Mm-hmm.
1,
Mm-hmm.
0,
Mm-hmm.
0, plus 1, 0, and then -1. Oh, the plus 1.
Plus 1. Okay? Net charge is going to be the same as the charge showing up here. And remember how we always assume those are neutral? Unless the charge is showing. Okay, so now, did I fool you? These isotopes of each other? These isotopes of each other? Why not, Nina?
Yeah, one's nitrogen, one's carbon.
Yeah? See, I tried to fool you by having the same atomic weight or mass, but that's not the definition. It's same atomic number, different atomic mass. So no, those are not isotopes. But if I go to these isotopes, yeah, this one is the regular one. This one is a heavier one, and usually the heavier ones are the radioactive ones. Having those extra neutrons seems to destabilize the nucleus. So carbon-14, they talk about dating really old stuff by the carbon-14 content, because over time it spontaneously decomposes, and you can see, you know, what your percentage is. That is section 7. Now, let's take a look at section 9. The good news is this is the only place that you have to pick up your calculator for the rest of chapter 4, 5, and 6, I believe, if I remember right. Yeah, Bruce?
On that top one that you crossed out,
Yeah.
that nitrogen would have been 6, could they have been isotopes?
Okay, but did
No, they're
nitrogen
not
ever
the
be
same.
6?
Oh,
Atomic
that's
number?
right, yes,
Yeah.
it would never be. Okay.
No, everybody's got his own atomic number,
So
or
they'll
he's a
never be
different
the
element.
same.
Yeah, that would never be the same.